In this video, we'll look at what are some of the challenges of storing your massive amount of embeddings in your vector database, and we'll also look at how you can optimize these embeddings with a very simple trick that can reduce your cost by over 32 times and also preserving most of your performance, about 97% of your overall performance that you previously had. So starting from this table, this is a table that tells you for these embedding dimensions what is your cost for storing these embeddings and how much cost will it take to operate them for a month. So at your first row you have a couple of models that stores vectors in dimensions 384, and to store about 100 million of them on a vector database it can take up to $500 per month. That's a lot already, and if you have to go upwards to 1 billion it can take up to $5,000. And this is, keep in mind that this is one of the most basic versions which with a very small vector dimension size. As you increase you can see your price exponentially shoot up, especially if you have a look at your last row, the embedding dimension of 3072, the OpenAI large versions, and to store about 1 billion of them it's taking about $43,000 per month. That is actually insane. So you can already see some of the challenges of trying to operate your very large RAG system in production, and storing these embeddings can be absolutely disastrous when it comes to your wallet. So binary quantization to the rescue, I guess. So what does binary quantization actually do? To think about this, we will actually have to sit back and think, how are embeddings actually stored in your vector database? So embeddings are usually stored in a float32 format, and the float32 format is quite simple. You use 32 bits to store your entire value or your numerical value, and out of which 23 of them come after your decimal point and 8 of them is your exponential part, that is the range of your total number that you can represent, and 1 is for your signed, so unsigned will not have it. So this is how you would represent the in a float32 version of an embedding, where I guess with a dimension of size 3, right? Okay, now what binary quantization proposes them is to simply threshold them to binary digits, and all it's saying is if your numerical value is greater than 0, threshold them to 1, and if it's less than 0, threshold them to 0. So this is very simple and intuitive, and you can see that the which was previously 0.123456, and after quantization all of your 3 digits have become 3 bits basically. And so what was previously float32 has simply become binary operators, which is almost 32 times reduction in your overall cost already, because all you need is a simple bit to store them. So celebrate, is it celebration time yet? No. If you think about this, so when we had embeddings that were stored in float32 representation, you can easily look them up using something called cosine similarity. You will embed your query, you will embed all your documents, and then you'll use a cosine similarity to try and look through your vector database. So what do you do if your values are just zeros and ones? How do you look through them? Hamming distance. So hamming distance is another algorithm. It's a very simple algorithm, to be honest, and this will only work if your two values or two numerical quantities that you're comparing have the same length. And essentially what it says is, let's take a value a or a string a and a string b, and your first assumption is they have to be of the same length. For example, in this example your length is about 5, and you will compare all of your individual corresponding positions, and every time the bits differ your Hamming distance shoots up by 1. So for example, you will first from left to right you're comparing 1 and 1, so no difference. 1 and 0, okay, there's a difference, so your Hamming distance increases by 1. 0 0, no difference. 0 1, 1 difference. 1 1, 0 difference. Therefore your final Hamming distance is 2, and the lower your Hamming distance, the closer is your embedding, that is the more relevant is your document. So this is also a very simple metric that you can use, or a simple algorithm that you can use to retrieve your documents. Now you can choose to stop there, or you can add an additional optimization, and it's called the rescoring step. So essentially what the rescoring step tells you is, you use your Hamming distance and you will retrieve some top k documents, top k binary documents. Along with that, you just use something called as a rescore multiplier. Let's think of it as a variable, and in our case, let's say 4, right? So if your top k was 5, 4 into 5 is about 20. So now you have 20 shortlisted binary documents. Now what you say is, instead of using your binary representation for re-ranking your documents, use the float 32 version of them, re-rank them, and using this now you don't have to use your float 32 representation of all your documents in your vector database. Instead, we only have our top 20 shortlisted ones, and now it's kind of affordable to use your float 32 version as well, right? I mean, it's only 20, so it shouldn't take a lot of time. And in highlighted, you can see that we're able to preserve, using this you're almost able to preserve 96% of your total retrieval performance, and you will also reduce your memory and disk space by over 32 times, improving your retrieval speed by up to 32 times as well. Also, if you choose to not have rescoring, you can also try and preserve 92% of your total retrieval performance. That's actually pretty good, especially for something as simple as your binary bits. So I guess it's actually time for celebration. Yay! There's also one more technique that you can use. It's called scalar quantization. This is also pretty simple and pretty intuitive. So instead of taking your float 32 and switching them into simple binaries, zeros and ones, you change them into int8 format. So from the diagram, you can see that your range is getting squished between plus 127 to minus 128. But you do this using something called as a calibration dataset. So what this calibration dataset is, your entire text corpus. So you provide it, and what the algorithm does is, it will first make embeddings for each of them, and it will take your maximum and minimum range of each of your embeddings, and then it will make very small buckets out of it. So for this technique, this is about 4 times lesser, because it's int8 compared to float 32, and this is also slightly better compared to your binary ones, but this will work only if your calibration dataset is good. So it has a little bit of risks involved in this as well, but if you combine both, you can see the best of both worlds actually. Like, you will able to retain most of the performance. So in the next part, we will try and implement before and after, and we'll try and implement this in code. We'll try and implement how it will work without any quantization, how it will work with the binary quantization, how it will work with the scalar quantization, and we'll try and combine both, and we'll see how the performance changes, and along with how long it takes to retrieve these documents. So the implementation for both binary quantization and your scalar quantization is very easy because of this library called sentence transformers, and I will be walking you through each lines of the code, and it will be pretty simple. So these are your generic imports. We're using 5Cs here for storing our vectors and your regular sentence transformers, and you have this function called quantize embeddings, which will be doing most of the heavy lifting for us. Usearch is also another incredible vector index that I saw, or an indexer, and I'm using it to store my int8 quantized vectors, and it's quite capable and super fast compared to 5Cs. The usage is very similar, so that's why I'm specifically using Usearch. I will link you to the page as well. So this is Usearch. You can go through their GitHub repo. The usage is very similar to 5Cs, but it is extremely fast compared to 5Cs. I'm using sentence transformer to load my large version of my embedder. So that will be our model that embeds all of our query vectors. And first I'm loading my dataset. It's a Quora dataset, and what this simply does is, it batches them just so I don't overload my RAM, goes through each of them and simply extracts out my text, and then you finally remove your unwanted columns. I'm setting a maximum corpus size of about 100k. So this one takes a while, so you might want to make sure that you run this without any errors. And this is my first query. So now all this is checking is, if I have any pre-stored indexes that are found, just read it from that. So we have a binary index which will be using to benchmark our binary embeddings. This is our normal embeddings that is stored in float 32 precision, and our int 8. So int 8 is going to use our usearch basically. So I actually have all of these. So I'm not going to be, so my if else loop is not going to execute. So this saves a lot of time. I'd already run it before once. It takes a good amount though. But anyways, so in the else part, what happens is I will encode my corpus, and there's a little progress bar here, and I'm using my flat index from 5cs. This is the normal one that stores your float 32 precision embedding. So since the embedder has vector dimensions of 1024, just add them and write it to my 5cs index. The second part is your quantized embeddings, and you want it in your binary precision. And then you take your binary precision and store it inside a separate indexer in 5cs called the index binary flat, and the same thing, you add it and you write it back to your disk. And for int 8 we will use the usearch index, and there's a couple of parameters that you have to give. It's very simple: your end dimensions and your data type. There are more. You can also choose the different types of clustering mechanisms, so you can go through the documentation, which I'll be linking in description. And the same thing, you just add them in your indexer and just save them to your disk. And there's a reason why I'm deleting it. So what happens is, when you delete this from your RAM, and when you load it back in a view, this will save a lot of RAM because you're only loading it as a view. So this is another optimization that we've done here. So search is the crux of the overall program, and we're saying that my top key is 20 and my rescore multiply is 10. So first we will embed our queries in just float 32 benchmark time for that, and quantize them to binary vectors. So we're also benchmarking or mapping, collecting time before and after. And once you have your binary embeddings, we're searching through our index for the top k and the rescore multiplier, and you will get two things that is returned, that is the scores and what is the specific id, what was the id or the match that was found in your binary index. And so you're retrieving the first one, and then again you measure your start time and your end time. So this one is for looking through your binary index, this one is for looking through your normal index, where you will search in your normal index for the same vectors, and you don't need this, so I'm just using an underscore because we are only interested in benchmarking the time. And this one is for checking the int 8 embedding. So it's a little different from the view. What you're doing is, since you've already found it, let's not waste time, and we'll just retrieve our best embedding, and then we're also going to try and benchmark time for that. And so this is the rescoring part when it comes to using it with int 8. So for int 8, what you have to do is you will have to run a matrix multiplication, and since the matrix multiplication, you just do a transpose here. And once you rescore it using your rescore multiplier, you have to sort them because now you've combined your float 32 along with your int 8. So we just sort them depending on from your lowest to your highest scores. So that is essentially what this bit does here. Arc sort from your top case, retrieve your indexes, and then get it from your score, and you just sort them, and this is where you finally return. You will return your scores, your indices, and how long it took for each operation. So how long it took for embedding, for quantization, your binary search time, your float search time, how long it took for loading, rescoring, sorting, and what is your overall retrieval time. And this is just simple while loop that will keep running as you keep giving queries. The program is quite simple, and now let's try and run the application, and let's see how bad or worse it got. So it can take a while to run this because you have 3 indices that are being loaded from your disk to your RAM. So okay, So we have response, and my query was, how do I become a good programmer? And what was our this thing, right? I think we tried to retrieve top 20 of them. Our top key was 20, and you can see these matches, and they are mm, sorted from your best to your worst, or from your largest to your smallest score. But what we are truly interested is the timings, right? So if you have a look at it, so embedding, it took about 0.5 second. Quantization, not a long time. The search time is how long it took to search through your binary vectors. It took only about 0.007 seconds for a corpus of 100k, so that's pretty quick. And your float 32 took about 0.01. You can already start to see the difference between your searching through your binary and your float vectors. And this is your load time, rescoring time. Sort time was almost negligible, and this was your total retrieval time. So you can already see that there is a big difference in your float 32 along with your binary vectors. But you can see that your results are quite good. Actually, I'm very happy with the results. All of them are excellent matches. So as your corpus scales, and these sentences are fairly small, to be honest. So as your corpus becomes huge, as your vector index or your embeddings become huge, you have big documents for RAG or very huge manuals, SOPs. When all of those comes into play, or your binary embedders and your scalar embedders can prove to be a big difference in your latency, like we saw in this program. So I hope you enjoyed this video. If you have any doubts, feel free to put it down in the comments, and I'll be happy to address all of them. So I'll see you in the next video. Thank you for watching, and bye bye.